Our book just covers limits in section 1.8, one section of chapter 1. I don't think that does it justice because it's a really foundational part of calculus, as you can see in that video you saw before this. It's plays the foundational role in understanding what's going on with both derivatives and with integrals. So we're going to kind of make our own little chapter out of this. So I'm going to call it chapter 1.8, and we'll use our book sometimes, but we're also going to supplement. So I'm going to first talk about just an informal understanding of what a limit is. And so, and then we'll get to the actual formal definition of limit and explore that in more detail in subsequent videos and assignments. So the notation and symbolism, we say that the limit as x approaches c of f of x is equal to L means, and again this is informal, as x gets closer to c, so as the x value gets closer to c, the y value gets closer to L. And that will serve you well. So we're going to try to understand this. So we want to explore and understand what this means in those 4 ways that we talked about. So we want to explore and understand this idea graphically, numerically, verbally, and eventually, because we're going to kind of hold off on the formal analyzing of this until the end. So analytically eventually. But I think we want to really get a sound understanding, a kind of conversational, I guess, understanding of this first. So we're going to explore a little bit, and I'm going to ask you, you can use your graphing calculator here. I can't bring that up on this video here yet, but I will talk about this in class. So, and I think on most of these I can draw a graph of it anyway, but we will explore that on a graphing calculator in the lectures in class. So the limit as x approaches 4 of f of x. So we can see, and I would say in class, or if you want to on your calculator, use x min, x max 1.7, and y min 1 max, and y max to 1.11. And actually, I'm going to change the equation here. Let's do 3x minus 2. We'll still do the limit as x approaches 4. So in a graph, if you do this on your calculator, I think you know what this is going to look like. It's going to have a y-intercept of -2, and it's going to have a slope of +3. So the line is going to be crossing the y-axis at -2. It's going to be fairly steep. And as we approach 4, so as we get out there to 2, 3, 4, so here's 4 on the x. So what we're saying is as we approach 4, by plugging in x values that are a little bit bigger than 4 and getting smaller, and as we plug in values of x that get closer and closer to 4 coming from below, any way we look at that, I'm going to extend this thing a little bit, then we know that the y values, so as those x values get closer and closer to 4, the y values are going to be getting closer and closer to 3 times 4 minus 2, which is 12, minus 2, which is 10. So that is what we are going to call that limit. That is, we will say the limit as x approaches 4 of 3x minus 2 is equal to 10. So we say equality because we're talking about the limit. Now, in this case, the actual function, actual value of the function at that place is indeed equal to 10, but that doesn't matter in terms of the limit. So the limit is going to tell us that it's getting closer and closer to 10, and whether the actual value of the function at that point is 10 or not is irrelevant in terms of the limit. Just the fact that it approaches 10 is sufficient. That's enough for the limit to exist and be equal to 10. So let's try another example. So this time I'm going to say that our function f of x is equal to x squared minus 1 all over x minus 1. Now, it's going to get the rust off a little bit from what we talked about in AP prep. If you recognize that x squared minus 1 factors into x minus 1, x plus 1, you can see that those x minus 1s are going to cancel. So back when we were in AP prep, we correctly said that there will be a hole in the graph at x equals whatever makes that 0, in this case 1. Hole in the graph, there will be a hole in the graph at x equals 1. So the graph of this thing is going to look like the straight line y equals x plus 1 everywhere except that there's going to be a blank spot at x equals 1. So we know what this looks like. I'm going to put the hole there. So it's going to look like a line with y-intercept 1 and slope 1, except that it's going to be missing that point right there. Now, does that affect, or how does that affect the limit? So again, we're saying the limit as x approaches 1 of this function x squared minus 1 all over x minus 1. Now we can see the function is not defined there, but remember, the limit says as we plug in x values that get closer and closer to 1 from either side, from coming in from the right and coming from the left, the y values are going to be getting closer and closer to 2. Now, the fact that the function doesn't exist there does not matter. We still say the limit is, in fact, equal to 2. So a limit is telling us what happens as the function gets closer and closer to that point, but it gives us makes no claims about what actually happens at that point. Okay, let's build on that. So now let's take that function, x squared minus 1 over x minus 1 that we just talked about, and we'll make it a piecewise function. So we're going to say that's what the function is going to be defined at everywhere except at 1, but at x equals 1, we're going to make it equal to 5. Now the question still for this function, what is the limit as x approaches 1 of that crazy f of x function? Well, we know what this looks like because we just graphed this over here. We know that the first part of that graph is that line with the hole in it. So that's this part that comes from right here. And now what our piecewise function is saying, at 1, instead of that blank spot, we're going to define it to be 5. So what we're looking at now is that graph of our function. So the question then is, we look at that function, does that limit exist or not? And if the limit does exist, what is the limit? Well, again, we're saying as we approach 1 from either side, those y values are getting closer and closer to 2, a y value of 2. The fact that the function is something totally different at x equals 1 makes no difference. The limit is still 2. The limit exists, and it is equal to 2, which begs the question, Does the limit ever not exist? Well, let's see some examples of where the limit can fail to exist. So let's look at the function f of x is equal to absolute value of x over x. Now, this is one that we will see a lot because it's a nice, or versions of this as well, are common examples of what we're going to see happening here. So this is one that we will kind of add to that list of known functions, what the graphs of known functions are. Now the idea here is it's going to be undefined at 0 because at 0 you're going to get 0 over 0, which doesn't exist. But for any value of x that is positive, the absolute value of a positive number is just that positive number. So if we plug in, say, 1 for x, we're going to get 1 over 1, which is 1. If we plug in 5 for x, we're going to get 5 over 5, which is still 1. If we plug in 20 for x, we're going to get 20 over 20, which is still 1. So for positive values of x, it's going to be undefined here. I'm going to change colors. I'm going to go with yellow. So it's going to be undefined right here, but it's going to be always 1 for positive values of x. Now, for negative values of x, the absolute value of, say, negative 2 is positive 2, divided by a negative 2 is going to be negative 1. The absolute value of negative 10 is positive 10 over a negative 10 is also negative 1. So what we're seeing is for all values of x that are negative, and again it's undefined at 0, it's always going to be negative 1. So the interesting question here is going to be what's the limit as x approaches 0 of this function absolute value of x over x. So again, what we're seeing as we come in from the right, as we plug in x values getting closer and closer to 0, at every point along the way here, this is 1. So we would say our right-hand limit is 1. Formally, we would call that the limit as x approaches 0 from the right of f of x is equal to 1. This notation is understood and acceptable. This is the formal notation over here. Now the left-hand limit, which we can abbreviate LHL, and that's commonly understood. Then as we come in from the left, this is always negative 1. And so we would write this formally as the limit as x approaches 0 from the left, using numbers that are less than 0, is going to be negative 1. So when the right-hand limit is not the same as the left-hand limit, then we say the limit does not exist. Does not exist. And we will use this so often, we will just abbreviate it DNE, and that is commonly known and understood and accepted on the AP exam as well. So there is an example of a function where the limit does not exist. Now let's look at another example. So let's go to our hopefully familiar 1 over x. And we're interested in what is the limit as x approaches 0 of 1 over x. So hopefully we are beginning to know just from looking at it, from remembering, adding this to our known list, that this is going to have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So as we approach 0 from the right, this thing is taking off and approaching positive infinity. So we could say the right-hand limit is positive infinity, or we could say it doesn't exist. Okay, because infinity is not a number. It is not getting closer and closer to a single number. Now, that's made the determination then, but I'm just going to point out as we come in from the left, it's going to take off and go to negative infinity. So we could correctly say it's going to go to negative infinity, also correctly say it doesn't exist. So the answer to the limit as x goes to 0 of 1 over x here's another example of where that limit does not exist. So it can fail to exist because the right-hand limit is different than the left-hand limit. It can fail to exist because it goes to either positive or negative infinity on one side or the other of that value of x that we're trying to determine the limit. Now, the last one is kind of a weird function, and I'll try to show you this in class, but you can try to explore this on your calculator. I'm going to tell you the window to look at, and then we'll still have to kind of interpret what's happening there. So a good window to choose, if you're going to do this on your calculator, is from a negative 0.1 to a positive 0.1 for the x-min and x-max, and you can go negative 1 to 1 for the y-min and y-max. Still, it's going to be a little weird to see what's happening there, but I'll try to help you translate what that looks like. So as what happens inside here, as x gets closer and closer to 0, this 1 over x, so as x goes to 0, the 1 over x, as we come in from the right, goes to infinity. So what's happening, this is sometimes called an inversion. But what's happening here, you don't have to know the inversion part, but what's happening essentially is that all of the stuff from 1 to infinity that this sine curve does, so you know a sine curve does this loop above, loop below, that wave forever. This 1 over x takes all of these infinite number of oscillations, all these infinite number of waves, and it condenses them into that space between 0 and 1. And then it takes all of the stuff between 0 and 1, this is the inversion part, and stretches that out from 1 to infinity. For us, the important thing to note is what's happening here on the right is this curve is going wildly up and down, is bouncing between 1 and negative 1 an infinite number of times as it comes in there. Now, at 0 itself, this thing's undefined, but no matter how small a little piece of the x-axis we take around 0, it's going to contain an infinite number of those condensed sine wave loops. And similarly, that's happening on the other side. We're getting more and more and more and more and more. So the idea is no matter how small a piece you pick around 0, it will contain an infinite number of these sine waves, very, very condensed. So our limit as x approaches 0 of this goofy function sine of 1 over x, it is not getting closer and closer to a single number. Therefore, the limit does not exist. And we're going to say this is because it oscillates. Okay, so there are going to be, we see a few different ways that the limit can fail to exist. When the right-hand limit is different than the left-hand limit. In fact, there's 3 ways. Let me just write that down. So 3 ways the limit can fail to exist. The first one is that the left-hand limit is not the same as the right-hand limit. The second one is it can go to infinity on one side or the other or both. It doesn't matter if they go to the same infinity or not. And the third way is what we call an oscillation. Very good. We'll build on this in the next few days.